So good morning, good afternoon, good evening, depending on where you are. Welcome to this webinar on using HIL to de-risk your renewable project delivery. I'm Etienne Leduc, Director of Product Strategy and Investment at OPAL-RT, and I'm really happy to have with me today Marty Johnson. Marty works as a power system engineer at EPEC Group in Australia, focused on the grid connection of large renewable projects. In collaboration with the University of Queensland's EPEC Group have developed a platform that utilizes hardware-in-the-loop testing to enhance certainty and power system security during the commissioning of large-scale renewable projects, particularly through a pre-commissioning setup and validation process. So that will be the two of us for the webinar today. The flow will be very simple. There's going to be a 25 minutes presentation from Marty, then about 15-minute Q&A session. So we should wrap up within about 45 minutes so that you have some time for a break and going to your next meetings. And on this, I'll give the hand to Marty to get started.
Wonderful. Thank you, Etienne. Yeah, good morning, good evening, and everyone. Let me just share my screen quickly. I just wanted to start off by giving a bit of a background about what EPEC is and what we do. So really what we're involved in is the connection of large renewable plants such as batteries, hybrid plants, solar plants, and also commissioning of wind farms as well. And really we're involved on the entire process. So this is from the concept stage where we do the initial connection assessments through to doing the actual engineering design, grid connection studies. Then we're involved in the EPC life cycle. So where we'll do the substation design and delivery, and then right through to the testing and compliance side of things. So we'll commission the solar farm and the control systems, and then we'll go through and do testing as well. And all of this currently we're doing in the Australian market. So we have the national electricity market over here, and EPEC's involved in connecting multiple gigawatts of projects over here. So I just want to kind of give you a bit of a background first of what a grid scale renewable plant looks like. So pictured we have a hybrid plant here, and realistically, what we're aiming to test is mainly the control system using the hardware in the loop. So what the control system basically works from is that we're trying to control this POC, which is the point of connection. And we do this by taking measurements at the point of connection using a power quality meter. The power quality meter then feeds the certain measurements like active power, reactive power, voltage, and frequency through to PPCs. So in this hybrid one, it's a 3 PPC layout, but typically on a farm, maybe you might only have one, especially if it's only a straight solar. And then these PPCs would adjust the commands to the inverters. So that way you get your desired active and reactive power at the point of connection. And then, of course, we have our energy storage or energy system on the left that provides the actual energy to those inverters. So what is a pre-commissioning platform? So we, as Etienne mentioned before, we originally had a research project with the University of Queensland, and what our aim was to develop a testing platform to really de-risk the deliverable process. When we're doing these farms, what we've noticed is during our delivery that we have the modeling stage where we go through and do our grid connections, but then once we get to the commissioning side, there's a number of issues which really could be that maybe they aren't modeled, and we'll go through a bit more what these kind of issues are a little bit later on, but they can really delay the timeline up to months at a time. And so really what we want to try and do is try and see how can we use hardware in the loop to pre-commission, especially these controllers, to try and de-risk this process. So how this would kind of work is that when we normally go through and we do our design of our plan and we do our modeling and we have our connection agreements with our NSPs and regulators, then we would go through and do a bit more of our detailed design. And when we're doing that detailed design, we'd be working with the EPCs or developers and OEMs to acquire that actual hardware that we want to test on the test bench. And then once we got that, we'd test that equipment against what in Australia we call the generator performance standards, but effectively it's just the set of rules that a generator has to comply to when they're connected to the NEM. And we would do this to kind of mimic the same kind of testing that we would do on site. Once we validate this performance and we'll benchmark it against our models, then we'll fix any issues that we come up with, and then we take this equipment that we've already pre-configured and validated, and then we'd send it straight off the site before commissioning happens. So how this works for our OPAL-RT setup that we have is that we really have mainly the high power components that we're keeping modeled in the EMT platform. So this is similar to how we would do modeling in PSCAD. We do a very similar thing in HyperSim here. So what we will do is we keep all of the high power stuff. So we're talking about transformers, reticulation systems, and the Thevenin equivalent grid source. And we still model that. And then from there, we use a power amplifier that we have, which will basically emulate what would be CTs and VTs at the point of connection that would scale down that voltage and current to something that would be applicable to the power quality meter. So typically this would be around 110 volts and 1 amp. And so those signals that are coming out, and you'll see our setup a little bit later, are the actual voltage and current signals that a power quality meter would see. The power quality meter acts as it will, provides the measurements to the PPC, which we have in the hardware as well. So this is all of our equipment on the right. And then that PPC makes calculations on that to provide that active power and reactive power reference that it passes back through to the inverter via the OPAL-RT platform. So realistically, we have this real-time platform. You can see at the top right, we have a OP5750 or 5650 rather, sorry, and that is included in our test bench. Then we also have a test bench which includes the hardware and everything there, and then the HyperSim model as well. So the kind of testing that would go through when we do these generators. So this is what we would typically test on site. So we test our reactive power capability, how the control system responds to voltage disturbances. We test frequency control for frequency deviations, active power control, reactive power control, voltage control, and communications failure. And so when we do this commissioning of a solar farm, it's required. It's called the R2 stage in Australia. And we'll do this commissioning, and then we test the compliance of the plant against what we've said it will do in the modeling phase. In the hardware in the loop, there's a few things that we can do that we don't actually get to do when we do our on-site commissioning that can kind of give us better confidence about the control system design. So firstly, we can replay network events. One particular event in Australia was the Curtailed event, which a large generator effectively blew up and resulted in a large frequency deviation. So we can replay these events through the actual controllers and hardware to see how it's going to respond. We can apply faults and make sure that the actual equipment that we have, especially if we're doing inverter controller testing, that they apply, that they work correctly as we've modeled. And of course, on site, typically how we do this is something called continuous monitoring. So we'd wait for a fault to happen on the network, and then we'd go back afterwards and test whether we've complied or not. We can also do real frequency events. So because we have the power amplifier there, we can effectively change the grid frequency to make sure that the power quality meter is actually measuring the frequency as we expect. And we'll talk a bit more on this one later, why that's important. And then lastly, we can test without risk. So when we're doing our commissioning phase activities, if there are issues that pop up, some of these issues can be quite large and lead to large oscillations, which can be seen across the network. So really one of the big advantages of hardware in the loop is that we can go through, we can validate it much quicker. And then also we're not, if there's any particular unknowns that we see that can cause these particular issues, we're not interacting with the grid, which could cause issues. So this is an example screenshot of how we've originally validated this methodology that we use. And so what we can see here is that this is a particular test that we perform, which is called a voltage reference step test. So this is where we are aiming to change the voltage at the point of connection. And so we do a 5% step. And then what we can see is that I have 3 signals plotted here. So the green one here is the PSCAD model. So this is what we have to develop as part of our compliance for our R1 package. before we get our connection assessment and before we do the commissioning of the site. So that's what theoretically the plant should do. The red signal that you can see is the site response. This was an actual measured response that we got when we were doing what's called hold point testing, or this compliance testing that we're talking about. And so you can see that already they match pretty closely. But the blue one there is what we've got from the hardware in the loop. So one thing that we can see is that the hardware in the loop response actually better predicts the actual site response than the PSCAD model. And the kind of aim for doing this testing is to try and see if there's any differences here, why are they occurring? And in this case, the reason why it's slightly different is most likely because of different communication delays that haven't been modeled appropriately. So you, of course, saw in that last image that, they benchmark pretty well, and this is great. But it can go wrong in a number of different ways. So first of all, if you're working with these models, a lot of these models aren't actual complete representation of their real world counterparts. So sometimes this can be parameters missing from the model, or additional functions that exist in the real hardware that don't exist in the model. I've also seen it the other way around, where there's stuff in the model that doesn't exist in the actual hardware. We can see misconfigurations, and we've seen this on a number of projects, that OEMs and installers can misconfigure devices. Sometimes we'll have parameters that get exported out of our simulation environment, and we'll have a parameter register. But then when it gets entered into the system, then there may just be one parameter that gets put in incorrectly. And then, of course, this can lead to large issues. And we'll go through a bit of this, and I'll show you in the demo how this can happen. A big one is communications phenomena. So of course, we have when we're doing our control system design, we have to consider the communications delay, and this can happen for not just for network delays, but also we have particular controllers there which will have particular loop times and cycle times, which aren't always modeled the best that they can be. We can also see on-site packet loss for poorly designed networks, or and the communication protocols that we have there aren't modeled. So there's still a significant de-risking exercise, because when we're dealing with a model environment, we're not talking about actual discrete packets that are going across. A lot of times it's continuous signals, and we're not talking about that interaction as well. So there's also a certain amount of de-risking that we need to do from an integration point of view. Speaking on the discrete signals, so we have these cycle times of equipment, measuring times, and these discrete kind of packets that go through. These can cause stability issues, and this is just typical kind of issues that you'd see when you're doing discrete controller design. So let's have a look at an example that we've actually come up with, and we've seen this on site, and this has been a test that we've done back in the lab. So you can see here on the top, this is the signal that we've injected through the power amplifier. So we're changing the grid frequency in this instance. At the start, we're doing a rate of change, and then you'll see that on the second graph, this is what the PPC actually saw. So you can see that the second graph definitely doesn't match the first, that it's all over the place. One of the issues is that when we downloaded the recording from the power quality meter, this is the third graph here. So the third graph, it looks like the first graph. This is what we would expect to see. And so when we downloaded it, we say, okay, this equipment's all good. But then in reality, when we actually recorded, because we still had the issue, so we had to troubleshoot a bit further, we actually saw that the Modbus communication was different from the recorded information. And so the PPC was acting on this bad information, which was causing just active power to swing around in directions that we weren't expecting. There's a number of different challenges that can occur that we see on site. So incorrect frequency measurements, like we just saw there. We also have seen that the power quality meters sometimes have variable delays. So this is something that we don't capture in modeling as well, is that sometimes we might see that a meter will respond in 30 milliseconds or 5 milliseconds, but sometimes we can see it up to 200. And then so when we have this kind of, it's like a normal distribution. So you see this kind of bell curve of these kind of delays. Sometimes you can't really capture what's going to happen when you start having events that happen at that 200 milliseconds, even if it's operating as per your model. Because, for example, what we've seen in some controllers is that when that 200 milliseconds, if their cycle time is lower than that, then all of a sudden you miss a cycle, and that can lead to large instability. We've talked about this parameter conversion between model and equipment before. Another example that we have is that sometimes we see that the model parameters are completely different to the parameters that you put on the equipment. Sometimes equipment will be in actual values, but a lot of the times models are in per unit. One particular example is a ramp weight that we were dealing with when we actually did our initial research project. And this is where the parameter was in per unit per minute. And then on the actual equipment, it was megawatt per second. So this is something that will can definitely lead to issues. So I have another item here. So really what we can see is that the dynamic response from these particular parameter issues can change quite significantly. So this can lead to large overshoot. And we'll go through a little bit later on and do a demo on exactly how this can kind of occur. We also have seen that we can have different frequency response with different PPC versions. And this is not just like necessarily around the frequency response, but it's also a larger point about we don't really know when OEMs are providing these firmwares to the equipment. A lot of the times you're just given it and you're told you need to use this version and then it's done. And then if there's an issue, you'll get the updated version and, you don't really know what's happened in between. And you don't really know sometimes if it's actually fixed the issue. One advantage that the hardware in the loop setup allows us to do is that we can go through and do this rapid kind of prototyping to fix this, to fix these kind of issues, which of course you can't do on site because we need to go through provide reports. Just trailing back to saying how we can't use the network as a test bed, we really need to make sure that the implementation that we're going to do is going to work. Whereas in the hardware in the loop environment, we're not dealing with high powers, so it's much easier to do this kind of testing. And the last part is that one of the largest sources of delays that we see is the integration of equipment from multi-vendor products. So this can be maybe the SCADAs developed by a different person to the PPCs developed by a different person to the inverter, or maybe we have hybrid systems. But a lot of the times, most projects have at least some level of integration from different vendors. And part of the reason why this can be an issue is because the integration of that equipment, they can do testing on that equipment for like factory acceptance testing, which only includes their equipment, but rarely does it go across the different vendors. And that's what hardware in the loop, especially in the way that we're using it as a kind of delivery platform, it's really useful for. So in terms of the impact on the delivery, so we have an example here where when we were commissioning a particular solar farm, there was a 2-month delay because there was a mismatch in the voltage step test, similar to the one what we saw before. And for a plant, this can be up to $50,000 per day in lost revenue for a plant of this size. There was also another example where there was a large, there was a mismatch and non-compliance when they were doing commissioning where there's a fault. That there's eventually a $57 million write-down on this project due to delays, partially because of this and partially because of other issues that happened during commissioning. So in terms of how do we know it works? Of course, we've done the research project, but we've also applied it to a real project as well. So we've recently done it for a 50 megawatt solar farm. It actually only just got energized on Monday. And we've gone through and successfully done this kind of initial testing, which has gone really well. And it's kind of proved that our hardware in the loop testing really does save time on it. So based on the delays that we've seen, we expected that the same kind of issues would probably have lasted maybe up to 5 months of delays based on our experience in other issues. Some of the things that we saw is that the hardware wasn't actually capable of running at the same loop time as it was in the models. The metering configuration, it's a brand new metering configuration, which theoretically should have worked fine. And in models, of course, it works fine. But then when we have the actual equipment, we noticed that it didn't work the same. There was unmodeled equipment that isn't actually included in the models. There's 2 extra controllers that kind of sit in the middle. These introduce further delays, which means that we had to slow down the controller gains. The model didn't match the hardware for the PPC. And then also just typical integration issues where that we had to resolve. So a lot of times with this hardware in the loop testing, especially in Australia, we have a connection to reform initiative where we're really trying to speed up this delivery of these large generators, because we're undergoing this renewable transition and we're really trying to ramp up the amount of renewables that we need to replace these coal-fired power plants. We have had the question about, where does HIL fit into this? Isn't this just going to add time into the order already, quite quite lengthy system, and our answer is really no. We already have a gap, especially in Australia, between our detailed design at R1 and when we actually start commissioning, which is normally around 3 months is pretty optimal. It's probably normally closer to 6 months. And our HIL validation normally only takes about 1.5 to 3 months. And this is to go through, set up all the equipment, do all the testing, and resolve issues as well. And what we kind of suggest as well is that the issues that we see in HIL are the same issues that you're going to see on site. So we're just really bringing those delays backward, back a little bit, so that way once you're actually commissioned on site, that you're not going to be, losing money effectively. So yeah, really what we see it as being important for is de-risking projects. We can provide better certainty around timelines for delivery and also the power system security and making sure that our control systems are designed better. So I'll go through and we'll run through a bit of a demo now. So I have kind of how this fits in to our system. So you can see from the power amplifier, these signals, if we just follow it around, unfortunately my graphic isn't set up the same way as my actual equipment. So it's coming in down the bottom here. So this is voltage signals and current signals. And then these go up through to our power quality meters here. So we have one power quality meter here, one power quality meter here. Those take those voltage and current measurements, and then also calculate active power and frequency. They provide those to this power plant controller over here. And then from this power plant controller, that sends the active and reactive power reference back to the actual system here, and then it will pass it on to the inverter, and then the inverters execute that. Makes the kind of power changes and voltage changes at the modeled system, and then those then go back through the power amp. So what I'll do now is I'll bring up, so this is the model that we have running at the moment. So this is very similar to what we saw there. And so really we have just a couple of things. We have our inverter down this end. We have a reticulation system and transformers here. And then this part here is our point of connection, and then our grid equivalent over here. And so this will provide our signals to our actual power amp. And so let's see, we can run a quick test and I can kind of show you the kind of issues that we expect to see. So bear with me 1 second. So this kind of image that we have up here is the same one that we saw before. And what we'll do is we'll do this kind of validation as we would do it when we're normally doing it. So I just have to align this. So bear with me 1 second and I'll get it ready. All right. So this demo is actually running live in our equipment in our labs. All right. So that's changing now. And so we just have to wait about 20 seconds for that data to come back to our system, because the simulation is happening on our OPAL-RT system.
While we're waiting for the results, I'll invite everybody to start posting their questions in a Q&A menu at the bottom. Feel free to start asking questions already, but we'll take them at the end.
Okay, so we see that it's come through here. I just have to do some shifting. So because the hardware in the loop is running in real time, we just have to do some aligning of the signals just to make sure that they start at the same time. When we set this up for our actual simulation, we have some automated processes to do this kind of work. Okay, that looks pretty good. And then we'll go through and do some analysis on it. All right, cool. So that's looking pretty good there to me. So this is very similar to what we had before. So you can see same kind of result is that the hardware in the loop one, better predicts the actual performance compared to the PSCAD one. And then what we can kind of see, so I want to show you an example of where this can actually go wrong. So what I'm going to do is I'm going to artificially change a delay in here. So currently it's set to, effectively nothing, but I'm going to just change this to 300 milliseconds. So this can be equivalent to maybe networking delays, or maybe it's an unmodeled controller delay that we, like a cycle time from an extra controller that we have in here. So I'm just going to change this and I'll show you what the kind of response can look like from it. So we'll do the same thing again. So just bear with me 1 second while I change this back to its initial operating condition. And I can actually see when I've changed that back down that it's already overshooting, but hopefully we'll get to see that in a second. All right, so I will run this. And I've made that change. And then we'll just have to do a little bit of aligning again for our signal once it comes through. All right, we can see it's gone up there quite a bit. That'll do. Cool. And now let's just fix the scaling on this so we can see what's going on a bit better. All right, so this is the blue signal is the hardware in the loop one again. So this is just by adding in a 300-second delay into the system. So this is something that could definitely happen. We've seen on a number of projects, and you can see that all of a sudden we start behaving really oscillatory and much more overshoot. So of course, where we typically would do this, we wouldn't have this site result to validate it. So we'd have our model result and would say, yep, that looks fine. And then we'd get our actual hardware in the loop setup going and would say, well, we're getting way too much overshoot, we're being oscillatory, and then we'd go back and do that tuning and testing and try and find out what the cause was. So of course, in this case, if it is actually something like this where it's actual inherent controller delay, we'd have to detune gains, which can lead to a whole process that can be quite lengthy. So it's really important to catch these early. I'll show you maybe just one other example of what can happen. So we talked about before about how just that parameterization can be quite difficult, and that when there's particular issues that happen where it's not transferred across properly, then we can lead to similar kind of results. So this can be something like, maybe it's a voltage droop parameter, or it can be gains. It can be even in the particular example that we had with our control hardware in the loop testing before, is that we noticed that the maximum Q limits, which don't exist in the model, actually affected the response of our equipment. But the one that I'll show you right now, and I'm just setting it up in the background here in the control page, so you'll just have to bear with me for a second, is I'll show you the effect of what's called a PT1 filter, which is just a filter that happens on the voltage, and I will just apply that. And this is an example that we've seen actually happen on a plant, and I'll show you the kind of things that can happen. All right, bringing this up again, and I'm just going to do a quick. Maybe this one we can just actually do on this screen. We probably don't really need to see it benchmarked, because we already know it's not going to be not going to work well. All right, I'll run this. And then this is just taking a little bit to update. All right, so this Q down here is really what we're interested in. So we can see here that again, that we're doing a step, it's largely oscillatory, and this is because we're adding a filter onto our voltage measurement over here at the PPC level. So even though the end results are saying that it's an overshoot, the cause is actually quite different for this particular version as well. So those are the two kind of demo things that I have done, and that pretty much concludes our thing. So I think we can probably go into questions if we have any.
Take back the hand for a message or two before. Still invite people to pose their question in the Q&A section, and we'll take it from there. For those who haven't done it yet, if you'd like to consider it, we still have a couple of our user conferences will be happening over the course of the next couple of weeks in UK, Middle East, Japan, South Korea, and India. If you're interested also to follow what we're doing, and check out our Power in Mind magazine. In the latest volume, we also had some more information from Marty from EPEC on their project. And you'll find it along with many other companies in the industry is evolving around the inverter-based resources integration. So feel free to check this QR code and subscribe to the magazine. And from there, I'll be going to the Q&A session. So as a first question for you, Marty, so you talk a lot about the HIL validation of the power plant controller, but what are your thoughts on the converter control? Do you use generic models? Do you work with black box models? What are your thoughts on using this together with the power plant control in your HIL testing?
Yeah, that's a great question. So with the um, included in the setup that we showed before, we didn't include the inverter control in the actual hardware. So what we've done is we just have that as a model currently. So this can be like when we do our actual grid studies, we have to use the OEM specific model. So this would be a black box DLL model for that. And it really depends when we come down to like when we do this testing, what we actually think is going to be a risk for the project. And we do this on a project by project basis. So what an example for this would be that we've commissioned a number of plants with a very large inverter manufacturer. The PPC is also from that same manufacturer. And we know that that equipment is, quite reliable. We know how it works and it's all good. So in that case, we probably don't need to include the inverter controller as we're not interested on the dynamics of that level. We see typically more of the high level one. The issue with having the inverter controller as well is that often you have to have the actual OEM's like R&D team support. Sometimes they'll only have one or two controllers like this in the world. But even for the example that I showed before, that was a generic inverter model that we've tuned to be the same as the actual OEM's model. So of course this comes with some limitations. Like we have to be really careful about what we're validating. Like we're not validating fault response. But when we're looking at on the order of, the kind of like 2-3 second timeline, we see a lot more issues happening from the PPC and SCADA integrations and all that kind of stuff. So that really kind of determines what we're going to include in. But on the other side, when we're bringing new products to market, for example, we're doing hardware in the loop, or we're going through that process at the moment for a DC coupled hybrid. That's something that we're really, we would definitely be pushing for the inverter control to be included in that hardware in the loop testing. So.
Fantastic. You also mentioned in your answer some limits in modeling. I wanted to look back on the communication issues that we were mentioning earlier. Do you have any best practices to share on modeling this, or are there any limitations and when you take into consideration these communication delays?
Yeah, so look, definitely, like a lot of the times, especially when we're doing the kind of like grid connection studies, is that we're quite removed from, like what the actual end product is going to look like, just as engineers, because that's really where my main kind of role is. But it's important to know that those effects that we make early on have those kind of impacts later. So making sure that you look at, like a lot of times in PSCAD, we'll just use the default model for doing the measurements, but that power quality meter actually has some delay in it. So making sure that delay is included for that, delay is included for the actual like PPC cycle time. Sometimes there's interim devices in between the PPC and the inverter. That's like, kind of like a PLC or a, RTU or something like that. Make sure that those cycle times are included in your models. That's really what it is. And it, like, so some like examples that maybe we might use 50 milliseconds for the initial metering delay, but it really depends on the specific equipment, and typically you can reach out to OEMs to find that kind of stuff, but it's just about considering it early.
Sounds good. Someone would like to have more information when you talk about the effort or the inclusion of HIL modeling in your process for the commissioning. You talked a bit about the calendar, but how is it in terms of real effort, or what are, compared to the alternatives you have to try and de-risk your commissioning, and what kind of benefits that brings you using that HIL versus the effort that you input? Maybe you want to expand a bit on
Yeah,
that.
yeah, for sure. So like traditionally, like I think hardware in the loop has a lot of history, especially in R&D and academia, but really we're trying to bring it more towards that delivery kind of focus. So we're really like what we see is that the kind of like what you'd normally happen is that that's what the whole commissioning process is for, like that kind of compliance testing, making sure that it actually works. The problem is that at that stage it's already too late. Your delays have impacts. So for EPCs that are actually doing the construction of the plant, LDs for them might be 0.5% per day up to 15% of the contract value. So we're talking about millions, of dollars like there. For actual owners, we're talking about for a single day that the particular lost revenue for that 100 megawatt plant that we're talking before might be 50K or something like that. So like that's a lot of money just for so all that we have to do is that we have to say for this hardware in the loop stuff, we only have to really save on the order of a couple of days, which is almost certainly going to happen, because of the issues that we typically see. So with the hardware in the loop modeling as well, a lot of the time, so like for example, for the equipment that we have there, you do have to have a little bit of a specialized skill set because you have to, at least have someone that like you at least have to have two kind of like parties, one that is familiar with the power systems background and the power system modeling, and then the other one who does the actual commissioning of the equipment, because typically they're quite of a bit of a different skill. But for the equipment side, the OEMs have to configure that equipment anyway on site typically, and of course in our business we've got both a commissioning team and our engineering and modeling team, so it's quite easy for us to do it. But yeah, it can be like one of those things that you do have to go through. But for the actual equipment itself, we already have to get that equipment in. So the OEMs have to provide that equipment for site. So what we're really asking is just ship it to us first. We'll do that testing on it. They do the commissioning there beforehand, before actually getting to site, and then yeah, we for the power system side of things, like for the actual like modeling side, we already have to go through and do that modeling in PSCAD in Australia anyway. So really, it's just converting from PSCAD to HyperSim, and which is a really straightforward process. HyperSim has a PSCAD to HyperSim conversion tool, or if you're using other platforms, I know that HyperSim has those as well. So yeah, it's relatively straightforward. Probably the biggest kind of area is really about that black box model that you were talking about before, and deciding, do we need to include an actual black box model for the HyperSim environment, which can be challenging, or can we do something like we use a generic inverter like we have done, and that still produces really good results when we're looking for that same kind of for that kind of validation. We just have to be careful about what assumptions we're making when we do that kind of testing and what we're actually validating.
Great answer, thank you. I'm not sure you answered that through your presentation. Many are asking more information on the IBR models that you have. So your hardware is the HPPC, PPC, but how about the plant model, the wind or PV models? What's the source of these models, or how are they modeled typically?
Yeah, definitely. So like in actual power system studies, there'll be, the actual OEM black box model. And this kind of goes back to what we're talking about before. In the example I just showed you, that's just a generic model that we've developed. And what we do is we do like this kind of staged benchmarking. So we have the OEM, like let's just say that the OEM doesn't want to play ball, doesn't want to give us a black box model for HyperSim. What we've done in this instance is that we've gone through, we've taken our generic model and we've taken their PSCAD black box model and just isolated the inverter out, do benchmarking for that particular like server voltage reference step, active power reference step, those kind of things, to make sure that the performance aligns, and then yeah, use that for the actual testing. Otherwise, we've also the project that I mentioned in the that we've just completed. That one we use the actual inverter controller. So the OEM provided the actual inverter controller, and so the interface there was at the IGBT level. So the IGBTs were still modeled in the EMT environment, but then the actual inverter controller was in the hardware. So, but we were also talking to a number of OEMs who provide those black box models, not only for PSCAD, but also for HyperSim as well. So, and if you're thinking about the source further back, It really depends on typically in Australia, it's common just to use for batteries, you just use a straight voltage source. And for PV, you might use a PV source, but it might not be really specific to the actual plant design until a little bit later. So yeah, again, it really just depends on your specifics. But what we've seen and we've already gone through is that in our experience, a lot of the issues happen at the PPC level, at the integration level, SCADA level kind of stuff. So that's where we're seeing the biggest delay risk. And in that case, we don't really need to detail the inverter models down to that detailed switching kind of model, unless we're trying to look at some phenomena that happens at that level. So for example, the DC coupled hybrid stuff, that's something that we're really interested in getting the actual inverter controllers there for.
Thank you. Next question. I'm unsure if I understand it, but maybe that rings a bell with you. Someone's asking, what's the ideal distance between hardware, mentioning that some OEMs are reluctant to release some hardware information.
The ideal distance, yeah, I'm not entirely sure about that first part. It is definitely true that OEMs can be reluctant to release hardware. What we're asking, or what we're talking with a lot of developers and EPCs about, is that just write it into your contracts, from the beginning. So if you just specify in there that HIL testing needs to be done, then when you have a big, multi-million-dollar project behind you, a lot of OEMs are much more willing to kind of allow that. At the end of the day, a lot of that equipment is getting purchased anyway for the site. So it's it's much easier at that stage to say, hey, we just want to get it earlier and test it first. And the more that we get on here, we're getting a lot of people coming up to us and asking for it. And as it becomes more popular, I think this will become easier as well.
Good.
Perhaps for that attendee, if I didn't answer the question about the ideal distance, perhaps if you could send it through again and just re-clarify.
Thanks. Someone's asking, is this control scheme that you prepared for the situation with the overshoot, is it extremely strict? I mean, can only an overshoot nominal for 1 second or no overshoot allowed whatsoever, or how is it?
Yeah, so for us, we have it's really, probably I'll be answering in a way that's really specific to the Australian market. We go through this kind of grid modeling process. So we have a number of rules that we have to follow for it. The overshoot isn't necessarily a thing in that when we're talking about the design, we do have to make sure that it's still reasonable, of course. But for the example, you still saw that in our base case, there was a little bit of overshoot. That's because we implement some inverter level voltage control for different reasons. But really what you'll do is you go through, you do this design, then you talk with the regulators about it. And then once you work with regulators, that's your plant performance that you submit in the PSCAD model, and they agree to that. So then from there, in terms of what the requirements are, is that we have another particular guideline, which is called the Power System Modeling Guideline, and you pretty much have to stay, there's a few caveats around it, but typically you have to stay within 10% error bands of your model solution. So we draw, for the ones that you saw before, we draw a 10% error band around that signal, and our actual site results have to stay within that 10%.
All right, thank you, Marty. We're reaching the 45 minutes. I'll take maybe just one last question that's quick to answer. What software is running on the hardware? The one you use is HyperSim. That's the one that you've seen in the demonstration earlier. And on that, I'll thank you very much, Marty. It was a very, very crisp and clear presentation. You're a great presenter. Thanks for your time. Thanks for all the audience to have stayed for the entire presentation. If there are a few questions that were left unanswered, we'll take them by email. If you have any further questions after the event, you can always reach out to us. And the webinar recording should be available within a couple of days on our resource center. And we'll be happy to see you in further events. Thanks again. Have a good rest of the day.
Thanks, guys.
Bye.